Bryn. My name's Bryn Divey. I'm a senior dev at a company called Nimbula. I've worked in Python professionally for about 10 years now, and I've been working with Twisted for my daytime job for 4 years. And what I do on a day-to-day basis is build what we call cloud-oriented operating system, which in effect is a product which you install in a data center and gives you an API which allows you to treat it pretty much like EC2 or Rackspace or another cloud system. Currently we're running at a scale of hundreds of machines. Our largest install is about 250 32-core machines at Yandex, which is a big search engine in Russia, which actually takes us at a bigger scale than the local high-performance computing system. So that's quite nice. When I say a distributed system, since we have these hundreds of machines, we don't want to run control nodes. We don't want single points of failure because we know that things are going to break. In large data centers, racks turn off, switches fail, hard drives go down. So we want to have our system running as a set of services which runs over every node we have available in the system. So basically what you have once our software is up and running is an API which allows you to launch virtual machines, connect virtual storage, create virtual networks, and have your virtual machines perform some sort of service, whether it be running a website or doing computing, scientific computing, number crunching. And everything we do is written in Python and Twisted, which is the one reason I'm here. So as I said, what sort of scale are we talking about? We've got 20 primary services which interact with each other. And I'm not sure if I started early. I thought this started at 1:45. But yeah, sorry guys. 20 primary services which run in the system, which intercommunicate to allow the system to run. And then each one of those services is replicated 2 to 15 times for redundancy. And then we have about 5 services which run on every computer in the system. And the problems we face is that we have a lot of internal communication between these services, and whether that be metrics, auditing, or just merely making requests of each other, and that there's a lot of vital security stuff happening. So I want to talk about SOA, as I said, REST, Twisted, and why we've chosen to use these concepts to build a distributed system. First, let me define a distributed system in the way we're talking about it, in a service-oriented way. Basically, there's no single control plane which does all the operations in a system. We have pieces which are responsible for certain aspects, for example, user management, management of data, management of virtual machine running, and these things interconnect over some sort of messaging bus. So service-oriented architecture is a term which Gartner claims they invented in 1996, although people dispute them on that. And it's styled as an architecture to build large resilient systems, often created by large numbers of developers who have to interact with each other and interact with each other's code. And the concepts here are to isolate responsibilities into separate services, to make sure that something which is dealing with a certain area of the problem is kept out of the way of everything else. Establish explicit boundaries of communication between these services so that the interface is well defined and there isn't too much extraneous data passing over. To have loose coupling between services. They aren't digging into each other's internals. To try and establish stateless services so that they can be bound onto, requests can be bounced from one onto another, and to make sure that there's discoverability, so everything knows what else is available and how to access it. Now REST, which you probably heard about a couple of years ago when it was very big on the internet, is representational state transfer. This came out of a guy, Roy Fielding's, I think it was his doctoral paper in 2000, and he was trying to design an architecture for the web, or at least formalize the architecture he saw coming out of the web. And the architecture he went for was for a way to transfer and manipulate representations of resources. And the best web applications are probably built on this sort of concept. It's a client-service architecture, which simplifies the implementation of both. Neither one has to maintain the state of the other, or in his case, he was looking at browsers and servers, so the server didn't have to deal with representation of a web page. That's the client's responsibility. It's a navigable architecture, which means that transitioning between resources was done using links. On the internet, it's hypertext HTML. You follow a link from one resource to another. It's stateless, because the server never carries. This isn't strictly true anymore, but a server should never carry a client's information from request to request. It should all come in from the client. And it's cacheable on conditions defined by the server. The additional things which make REST a beneficial thing to work on top of is that there's a lot of intermediary servers which can be placed on top of it. And the specification tries to say that a client should never be aware of what's between it. There might be proxies, caches, routers, but it will think that it's speaking to a server directly without having to know these details. There's also a uniform interface. Defined methods in the HTTP spec, they're get, put, post, delete, head, and a couple of others. And standard response codes, the 200 series for everything you want to write except for maybe this, 400 for you made a client error, 500 there's a server error. And having well-known content types allows the representation of resources across things to work nicely. Okay, that's a bit boring. Finally, Twisted, the last piece in the talk. Twisted was built by guys with names like Glyph and Itamar and Exarchin in 2001, so it's a lot less serious than Gartner paper. And it's an event-driven networking framework. What this means is that rather than either using a bunch of threads to handle responses which come in and do computation on them and respond, or to deal with any I/O source, there's an underlying reactor, which is a thing which uses a polling system. It's currently ePoll on Linux, which is a highly efficient select, and calls back into application code when something on one of these file handles changes, i.e. there's data received on a socket, someone's sending me a request, or I've got a response from my database. And the way that you interact with the system is basically you write callbacks to react to the results of I/O operations, then you perform another I/O operation, hook another callback onto it, and make this massive chain of these things. And while you're waiting for your I/O to return, your database to actually respond, something else can go and perform its computational needs, and you're still dealing within a single-threaded architecture. You aren't bursting out into multiple threads and trying to deal with the state transfer which happens there. But it looks like you're simultaneously serving multiple requests because you're blocking on I/O happening. So the other reasons Twisted is nice, it uses callbacks for future processing. It separates protocols and the underlying transports very nicely, so you could have HTTP over a file, or at least pretend to. And it's got a huge library of protocols and utilities to dig into. So the reason we chose these three things when we're trying to build a large system which has to be distributed across many, many machines is with service-oriented architecture, we're looking for modularity. New systems which we put into the larger system, new features which we build, are contained within their own service, and we don't have to disrupt existing code. We can leave it as it is and just add in new services to deal with these new problems. It also enforces good interfaces. As everyone knows, when you're writing code, it would be very good that everyone defined a clear interface between their areas of responsibility and only ever used that, but that doesn't happen when you have large development teams. When you're using service-based architecture, it pretty much enforces it, because there's a very well-defined layer of what's exposed to the network and what's exposed to other services. Services provide you with a lot of redundancy and scaling opportunities. When you've got hundreds of services running, failure is expected, and having multiple instances of a service which you can bounce a request to makes it non-disruptive. And also having services gives you a lot of freedom with regard to the implementation of your services. You don't need to stick with a specific language or a specific toolkit. If you've got a clearly defined interface, you can do it in whatever you have available. For example, you could switch down to C if you're doing a performance critical service rather than using Python. Choosing REST as our communications buffer between services was basically because it gives us a simple API to model mapping. building an API and designing what is available on it is a very hard task. And designing models and what operations out of the create, update, delete, destroy, and what actions happen from those is a slightly easier task. Also, choosing a REST interface forces developers to be harder on themselves when it comes to designing the API, and they often simplify things rather than throwing in new functions whenever they need a new function. Building on REST also gives you an ability to overlay industry standard HTTP stuff. So you can put a cache in front of your service or a proxy or round robin it using whichever method you want. And these are programs which you download, they're open source, they're well tested. So there we would have things like Nginx Varnish, which we can just put between our services and allow them to do their thing. It's also easy to add middleware like authentication, and also REST seemed like a good idea at the time. This was in 2008. It was pretty much the coolest thing on the internet, and we were designing then for wide area networks instead of local area networks. HTTP is the most routable protocol in the world, so if you're trying to talk to various things across the internet, you use HTTP. Finally, why Twisted? Which is more of an implementation choice than an architecture choice. And the first reason it was designed by guys with names like Glyph, Itamar, and Exarchan. It's a battle-proven framework when you're looking into Python frameworks. It now ships with OS X. It's used on very large sites. It gives us no threading complexity. We don't have to deal with deadlocks. We don't have to deal with shared state between threads. Our initial developers who started building the product, we were all Python devs, and we had some Twisted familiarity. So we thought that, this is probably the thing for us. We also thought that we could isolate new devs using thread pools and inline callbacks, which I'll mention briefly if I have time. Actually, let me just keep an eye on that time. So the design which we came up with for this distributed system was just to split up our services by concern. We have a user service which handles users, groups, and authentication, instances which launch new VMs and destroys virtual machines, storage services which strictly manage storage servers and attach block devices to instances, and none of these things share code or call directly into each other. We created a product-wide library of models that represent all of these objects in the system, the instances, the storage volumes, the users, and most of these objects have a very simple set of verbs associated with them: get, list, update, save, delete, which makes it easy just to write new models, write a meta class which pumps out your actual API. And then once we knew we would be talking over HTTP, or we could be talking over other mechanisms, we abstracted away the protocol and codec details. So everything which deals with adding a new user just receives a user model and some metadata about the request. It doesn't know that it's working over HTTP, doesn't know what it's dealing with. And it just returns a response or raises an exception. Details of the HTTP transport are hidden away from the controller, which allows us to swap out HTTP as an underlying backend for something like AMQP or SOAP or whatever else you have. This allowed us to create a library which communicated differently with different services depending on the context. For example, user.get in one place might call an HTTP call to the user service, and in another place, since it would be local to the user service, it would call the underlying database. So services are divided up to handle a subset of models, and routing between services is now, because everything's done over HTTP, can be handled by DNS names and URI components. So we start every request with a well-known internal endpoint, API.cloud, for example, and a front-end HTTP proxy can route this to an appropriate service. If I call instances.list on the front end, it's going to refer to /compute/instance. The proxy is going to rewrite that to compute.cloud, port 5001/compute/instance, and in this way, Nginx acts as a service bus. It figures out what sort of thing you're looking for, which service this is controlled by, and routes it to the appropriate place. This has given us independent scalability, so when we find that individual services are under pressure, it's very easy to start up new instances on new machines. And these are automatically load balanced using round-robin DNS, which gives us a nice way to handle fluctuating load demands. So as an example, just creating a new virtual machine, we need to know, does a user have the machine image, which just allows us to go get the machine image model, accept API unauthorized error, raise invalid. So that's happening within the local code. What this gets routed to is a bunch of HTTP calls, which are properly proxied to the correct services. Using the RESTful model, we know that unauthorized is a 401 return, 200 would be okay, and these get translated back to protocol-independent code. And with Twisted, it's quite trivial to parallelize these calls to multiple external blocking services. So if we're launching a new virtual machine, and we need to get machine images and storage volumes, and also check if there are conflicting instances on the local disk or on the local database, we can create a bunch of deferreds being the callbacks I mentioned in Twisted earlier, link them together, call them in parallel, and then our results only take as long as the longest one to call back. So in this way, we can call over multiple protocols, and using the Twisted interface, give ourselves a nice way to, without running threads, to call back into our code. So issues we've encountered with this particular type of architecture is, with service-oriented architecture, when you're trying to build in this manner, it's sometimes difficult to decide which service has responsibility over objects. There might be things which are quite cross-cutting in their positioning, and sometimes trying to find the correct place to put them is going to be difficult. Also, we've found that some actions require a significant amount of inter-service communication. So even though we've freed ourselves from having central control points, we're now losing a bit of that performance, well, losing a bit of the reliability by having a lot of network calls which we might have to retry and rebalance. With REST, some actions are difficult to model within a resource framework. So that leads to the creation of a lot of action-type models. Something request, reboot request, which doesn't actually represent an object within a system. It's just a convenient way of creating a request for an action. We found this quite serious with REST, that multi-object calls become really expensive. So doing 4,000 authentication calls, fetching 1,000 machine images, creating 1,000 quota objects to launch 1,000 instances within a single HTTP call requires 7,000 HTTP calls coming out. Each one requires a different connection. You need to pull these things because everything's over SSL. So times start building up. And using HTTP and REST means that you aren't multiplexing your connections. You're using a single connection per request, which might be given to something else if it's long-lived. But it just means that there's a lot of wait time where your inter-machine connections aren't being used. So yes, that's actually become quite a major problem in the design of these, what were supposed to be simplified systems. That slide's not supposed to be there. The button's not working again. And problems we've encountered with Twisted is in onboarding engineers, number one. Our problem area is that we hire a lot of low-level developers. Because we deal with a lot of network stuff, dealing with virtual switches, talking to kernels, a lot of the people we bring in have come from C backgrounds. Moving people across from strict C programming, system-level programming, to Python programming can sometimes be difficult. And adding an event framework like Twisted on the top makes it even more so. There might be 2 bad slides just after this one. No, good. Um, what I was saying earlier about using callbacks, I'm not sure if you're familiar with the actual term, but everyone's played with Node.js these days, so that's a good place to start. It just means that you have to break up all your code into a series of steps, which are split up by I/O operations. Now, Twisted and Python, using Python's generators, give us a lovely thing called inline callbacks, which makes one of these sets of separate callback steps look like a single pass-through statement. The problem with this in using Twisted's inline callback decorators is that to break out of a decorator, you use a yield, and normally when you yield on a deferred, it's just going to go and do something else and then return to your function. Forgetting a yield or the decorator on an inline callbacks function just makes things insane. If you forget the yield, it's going to go and start doing this in a separate thread of execution while your function continues. And if you forget the inline callbacks, you get terrible error messages, which tracebacks in your logs, which are very difficult to hunt down. So, at the scale, we currently have about 6,500 of these breakpoints in our system. Forgetting one of them is very difficult to find, and new users, especially to Twisted, make this mistake a lot. Basically, these sort of things require static analysis, which again is difficult using these systems. So some conclusions which we've drawn from this is that REST is a great system for designing interfaces. It's an amazing way to say, here's a model, here's a set of operations I have, and then use underlying and well-known transports like HTTP. But it's not so great for internal interfaces. If you get internal interfaces, your system's talking to each other on these sort of buses, perhaps something like AMQP would be a much better idea. But you really need something which does multiplexing on connections and which is easier to manage like that. So related to that, with this huge number of requests, which you find in systems like this, is you really need to be very aware of what's happening at the lower level. Be aware of what your connection pools are doing, how big they are, how many requests they have pulled up, and when a request timing out, and monitor these things and throw loud alerts. On Twisted, Twisted is an awesome framework. It's absolutely amazing. I've always loved it. But basically, if you're not writing a server which integrates IRC and mail and HTTP and half a dozen other protocols, actually that's a bit unfair, but if you're just using a single protocol and you aren't using half of Twisted's features, there might be other systems which are useful instead. G-Event is very beautiful. Been looking at that quite a bit. And which just isolate you from the explicitness of Twisted. And that's all I have for you. That was a very quickly prepared presentation. So if anyone has questions on these slightly disparate topics, I'm welcome to take them now. At the well, the caching situation, we found that not so much in our code, but in code which we talk to. For example, a lot of Java things have terrible caching policies. Some of the Apache Foundation's Java products, like Zookeeper and HDFS, tend to do a lookup at startup and cache IP addresses for the rest of the world to use. So we have had problems on some of that, but since we control most of our DNS policy ourselves, because it's an internal system, we're all right. I imagine if you're trying to do this on an externally visible system and systems where there are other DNS servers in the pathway, then you're going to find much bigger problems with doing round robin on DNS servers and doing reliability and doing redundancy on DNS servers. Failed services, well, we're aware of our services because they're single requests. Yeah. there's a much bigger layer underneath this which deals with a lot of this. For example, if machines go down, we use a system called Zookeeper, which has got ephemeral locks, basically, and we use these ephemeral locking mechanisms to reserve DNS names. So as soon as a service is actually down, it loses the DNS name. And if we have failures to a service, we retry and have a strict retry situation there. Anyone else? It's a, I hate this term, it came up from our marketers, a cloud operating system. It's basically software which installs on large data centers and is used to provide virtualization APIs, self-service APIs. So rather than going to a sysadmin and saying, I need a new 5 boxes to run this software, just creating virtual machines, creating virtual networks between them. I don't know, what's OpenStack? OpenStack is basically a set of defined APIs with some implementation done by different people at different states of completeness. We're our own API with some implementation, actually quite a bit of implementation done at some completeness. OpenStack, we're an OpenStack competitor, but OpenStack's looking interesting at the moment. There's been a bit of a backlash against it. But we perform a similar service.